assurance. So this is the names of the schedulers which we proposed along the years. There was the old AQuoSA IDF-based scheduler sponsored by the Fresco project, which is actually the scheduler on which the results, the experimental results that you can find in the paper are based. However, there are more recent schedulers, which are the EDF real-time throttling patch, also known as the EMOS real-time scheduler, in which we have this runtime and period configuration for each set of tasks. This is a scheduler for multi-core systems, so you may also configure the CPU mask or the set of CPUs, and you may exploit CPU sets and similar features. And it has a cgroup-based interface, so it has some problems which I'm going to talk about later. The sporadic scheduler instead is an attempt to keep having a priority-based scheduler, but implementing simply the sporadic server standard, which actually allows you to have some control of the temporal interference between multiple tasks so that you can have some degree of temporal isolation. So we implemented also the standard with a few problems just to keep the binary interface, to not break the binary interface of the Linux kernel. And also we have the more recent sched deadline, which also has a set of parameters, mainly the runtime that you need over each period, and a set of flags that control a lot of different variations on the semantics of the schedule. So what is the programming paradigm for using these schedulers? Well, you can have a few lines of code like this. This is, for example, setting up a reservation, a reserved task with a sched deadline. You simply set up what is your runtime that you want, what is your deadline, which is supposed to be maybe in a periodic real-time application will be your period. If your application is sporadic, then you may want to use the minimum interval period of subsequent requests as the deadline parameter here. And then you call schedSetScheduler by using the new scheduling class schedDeadline. And from here on, of course, I'm not showing the error management code. If the kernel answers OK, then you have the guarantee. But the kernel performs that very simple admission control test that I mentioned. So if you try to oversubscribe the system, you get an error. So you cannot really get the guarantees. Or you can use the EMOS scheduler. This has a cgroup-based interface. So that means that in order to create a reservation, we need to create folders into the cgroup virtual file system, and we need to echo some numbers into special entries of this file system. So this is how you would do that, pretty much the same thing that I showed in my previous slide with the EMOS scheduler. This is in the Bash language. However, luckily, we have also a library which is a compatibility layer with the old AQuoSA scheduler that allows me to do the same thing in a few lines of code again by using a convenient API call, which is more convenient when programming. OK, so sorry, the motivation was quite big because I needed to really give you some introduction about this. Now we go really to the work that we have been presenting in this paper. In a few lines, we modified Jack so as to use a deadline-based real-time scheduling policies with automatic tuning of the scheduling parameters so that the period is computing on the basis of the cycle duration coming from the Jack configuration. The budget is computing through a feedback-based loop, which automatically monitors the requirements of the Jack infrastructure and provides the correct amount of CPU. This required minimum changes to the Jack daemon and library. So we exploited, let's say, the design internal to Jack in having different classes. We implemented a separate Jack AQuoSA controller in which we implemented this particular binding with this kind of experimental scheduler available on the Linux kernel. And this requires no changes at all to the applications and clients of Jack. So an application that is already written simply keeps using the standard API. It doesn't have to do anything for that, for exploiting the new capability. And we measure the obtained performance of this. Again, shortly, we can say that there were no performance drop when running alone, and hardly can be, because, as I said, the classical environment in which we run Jack is by running Jack at FIFO priority or at scheduler priority on a system, so it doesn't get interference from anything else on the system. However, also when we run other real-time workload, we can do something slightly better than what it is normally possible with priorities, with priority-based scheduling. So how did we deal with the problem of Jack requiring CPU from different processes? As you know, in the Jack infrastructure, you have an arbitrarily complex direct acyclic graph of computations, which can be done in different processes. All of these computations need to complete within the next Jack audio cycle, and all of these computations also are part of wider processes which contain additional threads. So you may have graphical user interfaces typically attached, typically associated with each one of these threads. However, the balls I'm showing here are only the Jack client threads, so the threads that really are registered into the Jack infrastructure, and which are supposed to also to not get too much interference from the other stuff in the applications. So given that all of these computations need to complete within a given deadline, so I need basically a set of, I need a clear amount of CPU time to be available to the whole set of these real-time threads within a Jack cycle, then we basically decided to go for a single reservation defined for the Jack audio infrastructure. So we have the Jack daemon automatically creating in the system a single resource reservation, which is, as I said, a kind of temporal capsule. We can push, thanks to the hierarchical scheduling capability, we can put inside this reservation all the Jack clients threads which are registered. And also we have a feedback-based control loop, which is able to tune the budget queue depending on the observed requirements from the system at runtime. As I said, the period P can be actually computed simply by using, the formulas taking the sample rate and the buffer size of the Jack audio buffer, and the budget queue instead may be computed this way. There's a way of doing things. We did this way. How did we compute this budget? We estimated a percentile of the consumed budget distribution over a moving window. So a moving window of, let's say, the latest 1600, whatever it's configurable, the last number of Jack cycles. So we have the amount of budget that was consumed over the last cycles, and we built a percentile estimator of it, which may be as trivial as taking the maximum, or if you prefer, you take a percentile for just in the hope to get rid of possible spikes, which you don't want really to tune your computing power on. However, normally we add instead a safety threshold, so we do some over-provisioning, because what we observed in the past is not necessarily too predictive of what is likely to occur now on the next cycle. And also we need to temporarily boost the budget on new clients and also on X runs in order to, whenever they occur, in order to not allow further X runs to come right after. Also, sometimes, as I was saying, despite our effort to predict how much computing power may be needed by Jack in the next cycle, so despite our efforts to observe the past history, you may have a peak of the computing power in a real-time application. And I'm showing actually the coding times of an MPEG movie. Sorry, I didn't have a trace from the Jack running. However, the concept is very similar. Or anyway, consider a MIDI synthesizer. You may suddenly push 10 keys over a keyboard, and so you get 10 more voices, and you get a peak of computing power which cannot be foreseen, predicted by observing the history. So that's why you need not only to have some over provisioning, but even better, it's better to really run in soft resource reservation mode. That means that your application may be allowed to run for more than the allocated amount of CPU time over each cycle. So tasks may be allowed to run beyond budget exhaustion. And the budget, however, is still a minimum guarantee that nobody is able to remove from the application. Nobody can steal this minimum guarantee from the application. So in order to have this soft reservation behavior, we use the schedule reclamation of unused bandwidth, which simply redistributes the unused computing power of in the system fairly across the active real-time tasks.